Hello everyone, welcome to Professor 3 Mac. In today's video, I will show you how to perform design and analysis of automotive structural components in ABAQUS CAE, and I will show you in a step-by-step manner how you can do that. If you are familiar with automotive industry, then there are a lot of structural components which are involved in a normal car, and today we're going to focus on different types of pillars. So pillars can be classified as A, B, C, or D type pillars. And these are few of the car models starting from sedan to a estate car and then a hatchback. And you can see A type pillars are normally in the front side where they connect the roof with the body of the car. Then B type pillars are in the middle, and then the C type pillars can come, and then D type pillars, for example, for a estate car or for a van, is at the end at the boot. So what we're going to do, or what happens in the real life, is to design these kind of structural components. In this case, the pillars, we will be focusing on B type pillars or B pillars. So what you do, you basically create the geometry in real life. You apply different types of loads and perform experiments. You modify the material, thicknesses, and geometry to find the optimum size. But as you can imagine, experiments cost a lot of money and it requires a lot of time. So the best way to do is performing FEA analysis and use FEA to aid the experiment and optimize the structure with less amount of time and money. So that's what we're gonna learn today by using ABAQUS. What we will look at is we will simplify a geometry since the subscriber didn't allow to use the actual geometry. So I have created a simple geometry here. In reality, you do a lot of tests on it. So for example, in this case, they did 3-point bending test, as you see here, and they varied the thicknesses to find the appropriate thickness for this kind of loading. And then they also checked different types of materials such as steels and different types of components such as glass fiber reinforced composite and carbon fiber reinforced composite. So in this analysis, we will look at a couple of thicknesses, and also we will look at a couple of materials and see how you can change these in the model, and also how you can measure the forces and deflections and during the modeling, and to really compare different types of parameters, experimental parameters. So see you on the other side, and I hope you will enjoy it. Okay, so welcome to the software side of ABAQUS. So what you can see here is the same part which I showed you in the slides. So what I have done is I have created this fictitious part just to replicate the B pillars. And how I created that is basically, although it's out of scope for this work, we expect that you already have the geometry for that. But if you really want to learn, what I have done is I have used a sweep command. So I created a sweep path, which is basically goes down, straight, curved, little bit curved, then goes up. And then I created this C section, and then I swept it along that path, and I get this kind of section, which is kind of replicating the B pillar. So next thing we have to create a kind of a platen. As I showed you on the slide, there is a platen which will push it down for 3-point bending test. So let's go back here. Oops, and again. So here, and I will create a 3D discrete rigid shell and planar thing. So I will just create a circle and I will make it rigid. So that will push it down, as was the case in 3-point bending test. So I will call it part 3, but you can call it platinum as well. And I will create a circle now, so center, and then I will give a radius of around, let's say 0.033 meters, because everything is in meters. And if you look at the part now, so it looks something like this. I press done, and this is my part. So now I have to create a reference point. So I will go to tools, reference point, and then I create a reference point here, because if it's a rigid component, you have to apply all the loadings and boundary conditions on that part using a reference point. So whatever you do with the reference point will happen to the whole component, which is rigid. So now next thing is to define the material properties. So I'm going to go and define the material properties in the property module. And now what I'm going to do, I'm going to create the steel properties. So steel properties which are given to me, I will call it steel. And I don't need a density because it's not an explicit analysis which I'm planning to do, but in case if you want to do it, then you have to define density as well for inertia term. And the density given to us is 7800 kilograms per meter cube, since everything is in meters. For mechanical part, if I will define the elasticity, and elastic constants are actually given as the 200 gigapascals, so I need to give 9 zeros here. And also a Poisson's ratio of 0.33. Once I have created that, I can also give plastic part if I have plastic hardening curve. In this case, we are not provided with that, but we are provided with a yield strength which is around 384 or something for steel at 0.0 plastic strain. So that's what I'm giving here. So now our material properties are okay for steel. So now I will create a solid section, and that will be, in this case, it will be shell section, and it will be homogeneous because steel is homogeneous material. We are assuming it to be isotropic as well. And we need to now specify the shell thickness. So shell thickness, in this case, I am assuming it to be 0.3 millimeters. So I'm going to give a value of, let's say, 0.003, which is around 3 millimeters. So I'm assuming it to be 3 millimeters in this case. This is meters now, and I press OK. And now I will assign it to my B pillar, so-called B pillar, and I will say create section, select assign section. I will select the whole geometry here, and then I'll press done. I'll press OK, and now you can see the color has changed and the properties are assigned correctly. Okay, the next step is now to go and assemble the components. So I'm going to go to the assembly module and I will instance the parts. So I will first press the instance part button and I will instance these two parts. One is the pillar and the other one is the platen surface. And you can see platen surface is orthogonal, so we might have to rotate it, but I will keep it for the time being as it is. So now our components are here. Now what I have to do, I have to rotate it so that it becomes horizontal and it pushes it down like this rather than being in this direction. So I have to rotate this component around about x-axis. So I'm going to press the rotate button and I will select the instance. Then it will ask me to define the vector or axis of rotation, which is x-axis. So I will start with the origin as a starting point, and my end point will be any point on x-axis, which is 100. And now it's asked me for an angle, so I give an angle of 90 degrees, and you can see it's rotated and it's in the same orientation as the top surface. So now what I have to do, I have to move this part from here to somewhere here so that I can push it on this direction here. So I will press the translate object button. I will select the component and I will say, please move it from this point to this point. And here is my component now. So you see now everything is working fine. It is in the right location, but we need to make sure there is always some clearance between the platen and the top surface, because if it's meeting with each other, sometimes ABAQUS, especially standard, struggles to detect the contact. But if there is a clearance, then and when you move this thing down, then it's easier for it to track. In explicit, you have general contact, so you don't need to worry about that. But still, I always keep the clearance. Also keep the clearance as small as possible, because when you move it down, that will go without any calculations, and obviously you will lose some computational time. So again, you need to find the best arrangement. Okay, so our parts are in. I am happy with that at the moment. You can still move it down and close the distance, but I'm okay with this now. Now we go to the step module and we create a step. Okay, so let's create a step now. Press create step button. I'm going to do static general analysis. If it's a very short duration process simulation like a crash simulation or a very dynamic test, then you can use explicit as well. But I'm going to go with this static general in this case. So here I use geom. Total time is not important in this case because everything is rate independent, but if you have a string rate dependency, then you have to worry about the time as well, total time as well. I'm using a maximum time increment to be a very large number because sometimes if the maximum number of increments during the simulation goes above 100, then it automatically stops and then you have to restart. So on a safeguard, I just gave it a very large number. Initial time increment, I'm using my gut feeling and I'm giving a value of 0.001, while maximum I'm giving it 0.1, so that at least even if it goes 0.1 times time increment, then I will still get some more outputs and I can see what's happening during in between. So this is my step definition. I keep everything else as default. So my step is there. I'm not modifying anything about field output. If you want to change any outputs, you can go here and you can modify it. For interaction, again, we need to define interaction between the two. So we need to first define the interaction properties. So you can go here and you can define the interaction properties here. So we need to define the contact properties. Press continue. Here, and now we give tangential behavior as frictionless, and normal behavior I'm using it as hard contact, which is a default configuration, and this means the contact pressures will be computed based on the elastic properties of the contacting surfaces. So I will just save it now, and now I will go and create an interaction between the two surfaces. So I will create interaction by saying selecting surface to surface contact, and then I will select the first surface since it's analytical rigid surface and both are all our shell elements. So it will give us an option which surface. Top one is purple, bottom one is brown. So obviously we want to have brown surface. Just make sure make sure we can see that if brown surface is bottom, and yeah, you see brown is the bottom. So I will select the brown as the master surface, and also make sure that always the stiffer surfaces are master surface generally as per ABAQUS documentation. Now if you go for the slave type surface, then we have to select this surface here. So I will select this. Again, it will give us purple or brown. So you see purple should be selected because it's a top surface. So I select purple, and this will give us to this, take us to this window here. And what you see here is interaction property 1, rest is just default. So we just define the interaction and you will see that interaction is defined correctly. Okay, so next is now to go to the loading and define the loading. As I told you before, we're going to fix this and this end of the beam while we will apply vertical displacement from in on the platen. So I'm going to go to the boundary condition option here, create boundary condition, and I will select displacements. I have to select this whole area, so I'm gonna go to this view and I will say okay, select this area, whole area, and I'm gonna fix in all 3 directions. Great, easy peasy. Then I will do the same for displacement boundary conditions, and I will do the same on the left hand side of the screen, and I will press done, select U1, U2 and U3. Okay, and that's pretty much it. And now I'm gonna do the same for the platen, which will have, maybe we'll use reference point for the boundary condition. I'm gonna fix U1, U2, UR1 rotations in all 3 directions, while I have to move it down, so I will keep U2 free. And then separately I will define an additional boundary condition at this point, and I will give a value of U2 equals to minus 40 millimeters. Well, minus 40 millimeters is in millimeters, so we have to give 0.04 meters, and it should go down because we are going in a negative y direction. So this is how it looks like. And now we go to the mesh. So in the mesh module, we have to go to parts, and we will mesh this part first. So I will select a random. Again, you can optimize yourself. I'm going to use the default values here, and I will basically select the mesh size, which is this. So I think if you look at this mesh here, which is over a period, but you can again play around with based on your own geometry. You can partition. There are many tutorials on my YouTube channel on how to optimize the mesh, how to partition geometries, and control the mesh easily in ABAQUS. For the third part, which is this, we need to make it mesh again for rigid parts. Again, I'm using default sheet size, and then I'm going to mesh the part here as well. So when we have meshed the part, and if we go back to assembly in mesh module, then you can see everything is set up really nicely, and we have all the things meshed together as well. Okay, the next thing is to go to the job, and we will create a nice job. Let's create, and it will ask us for the name of the job. So we call it, let's say, B pillar, which is not appropriate. It's not a B actually, B pillar, but we just call it B pillar for the time being. And then precision wise, I will just go and use full precision to be sure with the values, and then I will press submit. So if you go to monitor, you can monitor the status of your job. This is a small job, so it will finish soon, but you can see input file processing went okay. All the data is correct, which we input, like material properties and contact conditions, and now it's running. And you see the running has finished with some errors. So this means something is wrong with your data. So we go. Okay, so I tried to rectify the problem. So for example, as I told you, properties should be defined appropriately. You always have to check that. So you see, I had to change the plastic properties to pascals. That's what I have done here. Also, shell thickness, I have used a value of 3 millimeters in this case, which is very small. And also, if you look at the loading, we need to make sure what is the total clearance between the two, because it has to travel this distance, and then it has to make contact and then go down. So for that, I have used a value of 0.04, which is still appropriate, and it is equivalent to 40 millimeters down in the downward direction. So when I run it, you can see it's finished without any problems, completed successfully. When you press results, you can see how the deformation looks like. So you can create an animation where you see it goes down, and then it basically how it looks like. Also, you can basically see what you see here is a lot of yielding, because 384 was a plastic yield strength we have used. So we need to modify the thickness and also the geometry to avoid these plastic regions, because we don't want our pillar to have plastic deformation. So what you can do now, you can go back and you can play around with the thickness. As I told you, you can play around with the thicknesses as well. And I'm going to use a very large thickness now. Let's give a value of 0.04, which is 40 millimeter thickness now. See what happens now. And I mean, most of the time when you have sharp edges and corners and these kind of thing, you have to modify geometry as well, other than not only the thickness as well. And some areas you can not only have to increase the thickness throughout, because it will increase the total weight of the part, but you can also reinforce certain areas where you have stress concentrations. So here you see there are some problems now. So let me see what is going on here. So what you see here is it didn't write anything, but it might be the case that the thickness is too large, that it is going out of this. As I told you, we use middle surface, so it distributes the thickness bottom and top, and that might have been causing problems. So I'm gonna go back and I'm gonna change the thickness to a limited value. Say for example, from 0.003, let's make it 0.009, which is around 0.10 millimeters or 9 millimeters. And hopefully this will work, because this is the problem with the shell, because you don't need the actual thickness. So hopefully this time it may work, or at least we'll go further. So you see it finished. We go to results, which is visualization mode, press the contour plots, and you see there is certain improvement. Some areas have reduced the plasticity size, but again, as I said, you might have to modify the geometry as well. So this is how you play around with the thicknesses, and you can find the appropriate thickness based on the model. Now next phase is basically go back. So next is now we go back and we basically replace the metal properties with the composites. So what I'm going to do, I'm going to use the same model because I don't want to waste time on it, and I will create a new model which will be called composite. So copy the model and I will call it composite 2. We call it 2 because I already had one model which I already tried on. So now what I'm going to do, now I'm going to go back properties, and I only need to modify the properties of this material. So I'm going to replace everything now, remove this, delete the material properties, but I don't need to delete it, but I can create a new material properties for the composites. So in this case, the density is given to us as 1600. Okay, so the next thing is the elastic properties. So elastic properties for this case will be requiring a composite anisotropic property. So I'm going to use engineering constants, and we are provided the properties as 7 gigapascals. So 3, 4, 5, 6, 7, 8, 9. I'm going to copy the same for E2, which is given to us, and E3 is 1 gigapascal. So I'm going to replace it with 1. Poisson's ratios are given to us as 0.22 in all directions. So I'm just going to believe what data is given by the subscriber. So I'm not going to challenge that. And here it should be around 1 gigapascals again. So 1 and then 9 zeros. Again, they should be different in different directions, but I'm just going to believe. So this is a properties which are defined, and now I'm going to create a shell composite section, and in this case I'm going to select, I can use as many plies as possible. So I'm going to use material which is composite and thickness of 0.003 and orientation, let's say 90 degrees, and ply name A1, material again 0.003, 0 degree, A2, and then I'm going to copy, I'm going to copy the whole row below. I will make 4 plies, so I'm just going to work with that. So another one, material 2, same 0.003, 0.003, and I call it 45 degrees, and then maybe a 90 degree or something. I'm just assuming something now. A3, A4. You can define like this, or you can also define properties using this ply option, and again it depends on you what you really want to achieve. So this one, and now if you look at that, then that is basically section 1, which is shell composite, and material 2 is used here. So material 2, if you remember, material 2 is, so if you look at this, then material 2, I will just have to select this. I'm just going to show you how it works, but done. And now section 1, material 2, which is shell composite, and that's done. So that's all what you need to do. You just have to modify the material properties with different layers, and the rest of the stuff remains the same as I did before. Step, I am not changing anything. Boundary condition, I'm not changing anything. So everything is the same. Interactions are the same as well, and hopefully it should work without any problem. So let's go back to the jobs. I'm going to delete this one because I'm going to create a new one now. Create, name is P, composite, so it should be pillar, maybe I'll just change it, continue, I will again select everything as default options, but precision wise I will go with the full precision. Press OK and then submit. So as you can see, it's now finished in no time, quick time. So I'm going to go press results, and these are the result files now. You see it's a composite file now, and you can see the stress distribution looks much different than previously. Previously these areas were yielding, but for composite with different orientation, you have a very much different behavior, but your stresses are very high. So you need to really make sure that, again, how many plies you need more reinforcement in this area, maybe modify the geometry, remove sharp edges, make it more round curves, etc. So this is how you can basically play around with this. And now you have seen that you can check this material with the other material. Also, if you want to plot, for example, how much force is required and what this deflection it is causing, then you can go to tools, and then you can say XY data manager. Then you press, so you just press create, select field output, continue. Then you select unique nodal here, select RF2 because it's in 2 direction, and also displacement U2 in 2 directions. So you select U2 here, and then you go to this tab element and node, and then you go to the node sets and select the reference point and then save. So we only have one reference point in this simulation, so I'm sure it will be the same one. So our data is saved, and now if you want to plot, combine them together, you want to plot force as a function of the deflection, which is vertical displacement U2, and you go up, press operate on XY data, and then you press combine. Then I will go with the absolute values because these are all going in the negative y direction, so they will be negative. So I'm going to go with the absolute value of U2, which is in X y direction, or on the horizontal axis, and also on vertical axis I want absolute value of reaction force, and I will save it as let's say for composite. And this is how, if you plotted it, this is how it looks like. I will delete this. So this is how it looks like if you see. Okay, so you see how this is how it looks like. Your displacement was your friction forces or force is 0, because until this point there was no contact established between the platen and the material pillar. But as soon as the contact is established, it starts to push it down. Your deflection is increasing, and also your reaction force is increasing, and you reach up to a value of 60 kilonewtons, which is very high force, up to a displacement of 40. I think so around this, about this area, your structure was already failed, because the strength of this material is around 100 something megapascals. So it was already failed around, if you just go down somewhere around here. So anyways, so you can see how you can do or play with this. If you want to plot for the other one, which was for the steel, we might already have that file here as well. I think it was this one. If it's still there, then you can also create the same data, and you can have a one-to-one comparison. So unique nodal, node set, reference point, save. And this will be very different than the elastic composite, because in this case we provided the yield surface, yield criteria or yield stress, but no hardening. So it will, your reaction force should increase, and then it will become constant because your material is already yielded at different places. In reality, you have a strain hardening, so you have some resistance there. So operate on XY data as before. Then I will use the combine option, absolute value, U1, U2, sorry, comma, absolute value, RF, save. and we call it steel. Oops. Steel. Okay, so we missed a comma here, so missed a comma here, so save again, and we call it steel. Okay, so now we have both. So if you plot both of them together, so we just press Control and select each of them one by one and plot, and you will see a big difference, as I told you. So you see reaction force is much higher in the case, for the case of steel, but then it saturates because we have yielding, and yielding causes no resistance and from the material, so it has it basically is almost failed. While in this case the force is always increasing because we model it as a linear elastic. So you can see this material has much less forces than this for the same deflection value, so this might be more suitable, or you can find it out yourself later on. So I hope this makes sense. You are now able to understand or perform structural analysis of different types of pillars in the automotive industry, and you can vary the thicknesses, you can vary the boundary conditions, and you can also vary the geometrical parameters such as thicknesses to find the optimum configuration. So see you in the next video, and please comment below if you like the video or if you want me to have something else which is in your mind. Thank you very much, and bye for now.